We're not going to go into a great deal of detail at this point with the nature of this solution, but we will take a cursory look at what happens. So one thing we want to consider is what would happen if gamma was 0. Well, if gamma is 0, that means we don't have any drag force, which means that the pendulum is going to behave as an ideal pendulum, and that's a problem that we recently solved. So let's just see. If gamma equals 0, not the best gamma I ever made. Okay, if gamma equals 0, then what? Then R equals 0 plus or minus the square root of 0 squared minus 4g over L, and I lost my 1/2 here, and that simply equals the square root of negative g over L. You can worry about the algebra of that, but that's going to be, and this is going to be plus or minus. We get plus or minus the square root of g over L times I. This agrees with the solutions we got for an ideal pendulum without any drag force. Just to make sure we see the connection, our solutions are going to be a e to the square root of g over L I t plus a, well, let's say b e to the negative square root of g over L I t. I'm just going to put an etc. down there. You can review how that works out. We're going to use the Euler identity. We're going to have sines and cosines. We'll let omega equal the square root of g over L. And proceed just as we did before. Now another important solution, the one that kind of serves as a demarcation between the real and imaginary solutions we're going to get for the square root. The discriminant, gamma squared over m squared minus 4g over L, might be 0. If that's the case, then R is going to equal simply minus gamma over 2m. Our solution is going to be x of t equals a e to the minus gamma over 2m times t. This solution is simply a decaying exponential. If we draw the graph of x versus t, we start at x equals a and simply decay exponentially with some time scale that's easily determined here. This x value is going to be greater than 0 for all t. If we think of the pendulum, this means, of course, x is greater than 0 on this side, x is less than 0 on this side. So the pendulum is going to be released from some point, and it's simply going to exponentially approach the equilibrium position. It's going to simply relax back toward equilibrium, but it's never going to pass equilibrium. And I should have noted this is the case for A greater than 0. A could be less than 0, in which case the pendulum would be released from somewhere on the left and approach equilibrium from the left. The exponential approach would have a constant half-life. That is, whatever time it takes to get from here halfway back is going to be the same time it takes to get from the halfway point halfway back from there, which would be to the quarter of the way point, and so forth. The thing will approach twice as close to the equilibrium position in equal time intervals.